OLS or ordinary least squares regression? What do we do in OLS?
Sir, we have a loss function and we try to minimize that function using some gradient descent or the normal equation or
Okay,
whatever.
so and what is that loss function?
It is some it is the mean square error.
Between what?
The original my original labels and the predicted labels.
Right. So original level, so like basically in case of least square ordinary least square regression, we have a for every data point xi, I have an original, or instead of original, let me write true level, and I so I like compute the difference between the true level and the predicted level, which is which I denote by this y hat, right? And then this whole thing I take the summation over all the data points for the set I am considering. Right, now in case of linear regression, what is yi hat? What is yi hat in case of linear regression?
W transpose X.
W transpose X, right? So basically, so the problem which I am solving here is there is the loss function is defined in the following way. Right, now we said that this loss function, like if we choose a W for which minimizes this loss function, then what happens? Then of course the like we will be able to reduce the or minimize the errors which we are making on these levels. But but if there is some special structure which I want on W, then there is no way that this OLS regression guarantees that to me. So what do I want? So what do I do? I add another function which I call as the regularization function in the following way. So this function f, this I call as a regularizer, and from this arises the term regularized regression. So this lambda is a parameter. It's a free parameter which the user can tune. So by tuning the parameter, we can increase or decrease the relative importance of the regularizer with respect to the OLS. So this is something which we call as the empirical loss. And this is something which we call as the structural loss. So as we discussed through various examples yesterday, if the I may choose a W for which the empirical loss is low but a structural loss is high, or I may also choose a W for which it's the reverse, that is the empirical loss is high but the structural loss is low. So between these two, which will I choose? I will choose that one for which the that is I will choose it according to the relative importance which I give to these two things. The regularizer function is such a function which will which will take a low value if what? When will regularizer function be take a low value?
And
If
W
the
and
If W and
W
W not are similar.
That is a particular case which we discussed yesterday.
When it has a particular
when
Yes, like when we do a so if regularizer like if W has the desired structure that I am interested in, then the regularizer should take a low value. But if it does not have that structure, then it should take a high value. Okay, now if that structure is W is close enough to W naught, as we are discussing yesterday, that's a special case. It can, the desired structure can be something else also. So like let us say that low if W has desired structure and high otherwise. Okay. So like for the same or for the same data set, keeping everything else constant, you can see that by changing this parameter lambda, you may end up getting different values of W as the optimal solution to this problem. So this again I will leave it to you as a mini project. I will tell you like what exactly the mini project is. Just bear with me for a few minutes. But before that, let us consider what are the different kinds of structural properties of W which we may try to impose with the help of a regularization function like this. So yesterday we saw an example. What was that example? May is property or structure, or let me call it as SP. SP means structural property 1. What did we consider? W should be close to W naught. Okay, so where W naught is my favorite vector, and in that case the FW is, as we saw yesterday, is nothing but W minus W naught, the squared L2 distance, or the squared Euclidean distance between these two vectors. So just to remind you once again, this square need not have been there. That is, even if the square was not there, then also concept wise it would have been fine. But I keep this square for the simplicity of mathematical computations, because I will solve this problem by differentiating with respect to W and equating it to 0, solving an equation, etc. So the carrying or calculating those derivatives will become much simpler if we have the square rather than if we don't have the square. So for that mathematical convenience, I put the square here. And we also saw yesterday that if W naught is the zero vector, that is a d-dimensional zero vector, then basically this constraint means that like all the dimensions of W should be small, should be as close to zero as possible. Okay, so that which is what we had initially talked about. That is, I had suggested yesterday and previous class also that in for various situations, especially if some of the features are noisy, then I would like to have low value of some of these coefficients. So that is an end which may be achieved if we set W naught to be the zero vector. And in that case, this problem boils down to what is known as ridge regression. Right, so the details of these are all given in the notes that are shared. I hope you are going through them. So just to say this, the expression for ridge, or the loss function for ridge regression is defined as follows. Here this is the empirical loss as usual. And this is the structural loss. Right, and you may note that this W norm square, sorry, not zero, this L2 norm square, this can also be written in the following way: W transpose W. So you can just like convince yourself easily that W transpose W is nothing but the squared Euclidean distance between them. Okay, just convince yourself. So once this is the case, you can, once we have written down the loss function in this way as we did yesterday, we can actually carry out the derivative of this thing with respect to W and equate it to 0, and we can solve an equation and get an expression for W. And as we saw yesterday, that expression for W came to be something very similar to what I get in case of OLS. So in case of OLS, the expression I get for W is as follows. If you remember, xi transpose summation over all the n data points which we are considering. So again, just to remind, this is a D cross D matrix. Okay, and then once you get the matrix, you take this thing. What is this? What does this cross mean? This is the Moore-Penrose pseudo inverse. This we multiply by this kind of quantity. Right? Now this quantity can also, what I have written can also be written in a slightly different way, like as we discussed yesterday. Can write it as x transpose x pseudo inverse x y. So you can so where the sorry yx, or was it xy? So no, sorry, this y is a n cross 1 vector. This x, this is a d cross n vector. This x so basically these x is a sorry, it's not it's a matrix. So like basically it's such a matrix where every row stands stands for a feature, and every column stands for a data point, right? So so you can just write, you can just check that you can write this thing in this way also. But for the you don't need to look upon it this way, you can look upon it this way also. Now if we consider ridge regression, then the expression you get for it is very much simpler, or I mean sorry, very much similar. Minus. Okay. So you can see that this factor of lambda I is the only thing that is the difference between linear regression and ridge regression, where I is of course the d cross d matrix. Okay, d cross d identity matrix. So this is the solution to the problem of ridge regression, and it is going to give you such a W where with respect to compared to the W which you get from for OLS, let me call it as the W subscript OLS, and this way the W which we get is W subscript ridge. Okay, so you can actually carry out an experiment and you can see whether or not the W ridge has smaller values compared to I mean the smaller absolute values compared to WOLS. Okay.
Just to clarify, ridge regression is when W naught is the origin.
W naught is the origin. If W naught is the origin, then this problem,
Okay.
this kind of the squared L2 norm regularized regression is known as the ridge regression. So and the expression for ridge regression is this thing. If instead of like if instead of the origin, if you had considered some other value of w naught, then also like just one extra parameters somewhere with lambda w naught or something like that will come in to this expression. It will not be very significantly different. That expression also we had derived yesterday, so you can just check it for reference. Now, so this is the
Sir, can
structural
we say
property.
that,
Sorry.
sir, can we say that the W derived from ridge regression is always like 100% of the times better than that derived from OLS?
There is nothing called better or worse. It's like you can say that like if for a suitable value of lambda, the ridge regression, the w for the ridge regression will probably have smaller will have smaller elements than the WOLS. This in other words, if you take consider the L2 norm, or the squared L2 norm of WOLS. Just a second. And if you consider the L2 norm of W ridge, then you can be sure that this will always hold. That is, the OLS, the W you got from OLS will have a higher L2 norm than the W from ridge regression. Why? Because in case of ridge regression, we have actively tried to minimize the L2 norm of the W with the help of this function, which we have not done in case of OLS. Now, this will of course be compensated with a loss in case of accuracy. That is, the accuracy of the predicted level will of course have to be compromised in case of ridge regression compared to least square regression. So we can say that while ridge regression is likely to give you a W which is small, which has a smaller L2 norm than WOLS, but at the same time the error which you will incur in this part in case of ridge regression is likely to be higher than the error which you will incur in case of OLS. Now the amount of difference in the L2 norms as well as in the error will depend on two things. One is the nature of the data set, the other is the is this lambda. Now it may happen that on some data sets you may be lucky that the WOLS and W ridge are actually the same. If you are really lucky, that will happen. But that's a rare situation. In most cases, it will not happen. Now, so between OLS and ridge, whichever is better or not, that depends entirely on your relative understanding of what is better and worse. So you like depending on your situation, you may consider reducing the empirical loss as a higher priority, or you may consider reducing the structural loss as your higher priority, and that is how we'll understand what is better and what is worse. Now, this is, let us consider one more structural property, and that is sparsity. Now, what I mean by sparsity is that W should be sparse. Now, what is meant by W should be sparse? Is sparse, meaning most of the elements of W are 0. So when I am like when I am doing this operation, that is when I am trying to predict y from x. Now if most of the elements of W are 0, then what can I say about this prediction? Suppose W is sparse, most of the elements of W are 0. Then can we make some general comments about this equation?
So gives it gives us the feature importance of the features, that if some feature is irrelevant, then its weight will automatically become zero.
Exactly. That's the right answer. So like if I put many of the elements of W to be 0, the corresponding features will become basically irrelevant. They are whatever values they take will no longer be relevant in our prediction of Y. So in other words, it's like I am predicting Y now on the basis of only a small number of attributes in X. X is giving us d number of attributes, or rather d minus 1 number of attributes and a bias, but I am not using most of those for my prediction. Instead, I am selecting only a small number of those attributes, which may include the bias also, for my prediction. So this is, like, in a sense, what I am doing is called feature selection. So if if the structural property which I desire is that W should be sparse, then for that what I have to do, I will have to formulate a new kind of regularization function, which takes a low value when W is sparse, and it takes a high value when W is not sparse. Okay. So just to remind you, yesterday we had defined a set of functions known as the norms of vectors. So I had defined something known as the L0 norm or the L0 norm. So can anyone does anyone remember what that L0 norm was?
Yes, sir. How many non-zero elements are present in the vector?
Right. So if W is sparse, will that L0 norm, will it be low or high? If W is you gave the definition of like L0 num, correct? So if W naught is sparse, then will this be high or low?
Low.
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 So if it is sparse, then this is low. Else it is high. So then if I use this as my loss function, will that work? Suppose I am using this as my regularizer. Sorry, not loss function, I mean regularizer. Is this a this satisfies the definition of regularizer? That is, whenever the desired property is satisfied, then my regularizer function should give a low value, and if property is not satisfied, then it gives me a high value. So in case of sparsity, this is true, because whenever the matrix is sparse, then this gives me a low value. Whenever matrix is not sparse, sorry, whenever vector is sparse, then it gives me a low value. If not sparse, it gives me a high value, right? So this is the like, in that case, this becomes the equation or the function which I want to minimize, right? This becomes the new definition of my loss function for feature selection.
So
Yes.
here you're saying that the magnitude of W will be low if most of its elements are 0, right?
No, that I am not saying. I am saying that if most of the elements are 0, then its L0 norm or the L0 norm of W will be 0. This is the L0 norm of W, and it's defined to be a function which takes low value that is, this is basically equal to the L0 norm of W is equal to the number of non-zero elements. That's all I have said. I am not saying anything about the magnitude of W. So it can happen that some elements are, or many elements are 0, but there are some elements which take very high value. That can happen. That I am not making any comment about that. I am just saying that I want such a W where most of the elements should be 0. I am not saying any specification about the overall magnitude of W or about anything else. So now if I want to find W, then I run into some trouble, because unlike the previous case, I am not able to able to calculate the derivative of this loss function with respect to W, because of the nature of this function. So as you can understand, this is a highly discontinuous function. You will not be able to derive it. Now, so since you are not able to differentiate this function, so then what we do is we do a relaxation. What I mean by relaxation is that instead of using this non-differentiable function as the regularizer, I replace this with another regularizer, which another alternative regularization function which is differentiable, or at least which about which you can like which you can solve with the help of an algorithm, but it will not be very, its value, the value which that new function takes will not be very different from this value. So so that the alternative which is taken here is, instead of the L naught norm of W, I take the L1 norm of W. So now that is to say, the relation between the L naught norm and between the L1 norm, there is a particular relationship between those, but like it can be verified that that is like in a sense you are trying to make sure that is if you are able to bound the L1 norm, then the L naught norm you will all like you will be able to bound as well, because of certain certain properties related to these vector norms. So this again will be part of the mini project which I am going to tell you right after this. So so this is the relaxed version of the sparsity problem. Now while if you solve this problem, I mean solving this problem, as I said, is difficult because you cannot like apply any of the known optimization algorithms, but if so what you do is you relax it to this problem, and this you will be able to solve. Then you will, the W which you will get, let me will like that, it will have it will have such a property that most of its elements will be close to zero. So you here you were expecting most of the structural property you originally wanted is that like most of the elements of W should be zero, that is W should be sparse. This what it will do is that it will make sure that most of the elements of W will be close to zero, even though not exactly zero. So then once you get such a W, then it is up to you to define a threshold and like remove all the elements whose values are below that threshold. But so that is a post processing which you may do. So the now when I come to this problem, when I come to this equation and I want to minimize this new loss function, in this case also I will not be able to do much if I try to take the derivative of this loss function with respect to W and equate it to 0 and then solve. I won't be able to do much because of, again I will run into trouble by when I try to differentiate this quantity. Just like I had ran into trouble, like I had said that if I try to take derivative of just the L2 norm, then I had some trouble. So that is why I decided to put it take it as a square. But in this case, taking the square also will not help. So will I basically it will be difficult for me to take the derivative of this and equate it to 0 and solve. This I will not do. So instead what I will do is I will use some numerical optimization technique. For example, some of you have been already been talking about gradient descent. So like gradient descent is one example of what of a numerical optimization problem. So but gradient descent we will come to at a later stage. So as of now, let us just say that this problem I can solve with the help of numerical optimization like gradient descent. So once I solve this problem with the help of numerical optimization, the W which I like this is done or this particular problem is sometimes known as the lasso problem, LASSO. Okay, it's a basically an acronym, so you can read a bit more about it later in your for your mini project. Uh, so this is this I call as the lasso problem, and the W which I get from it after applying the gradient descent, I can denote it by W lasso. So this will have most elements close to 0. Okay, most elements close to 0, not exactly 0 as I would have expected, I would have wanted originally, but most elements close to 0. So then you can just prune away those elements which are those elements which you think for which the magnitude is below a threshold, so that from that you can do some post processing and you can get the sparse vector that you wanted. Then that's basically after, so basically after like one more step which you have to do by yourself, you will get the sparse vector that you want. Okay, so now we have got three possible ways to estimate the W. The first is the WOLS, which simply minimizes the least square without any structural property. Then I talked about W reach, which basically gives you a W where all the elements are small or bounded, while also trying to minimize the loss, the error. And then I also talked about W lasso, where where you get a W where most elements are close to 0, while also trying to minimize the error. So the this story of the lambda parameter which we discussed yesterday for ridge regression is also valid in case of lasso regression. So once again you are making here, with the help of the lambda, you are making a trade-off between the between the empirical loss and the structural loss. So here this is your empirical loss, basically suggest quantifying how well you are able to fit the data, and this is the structural loss in which is indicating how how suitable the W is for your application. Okay, again, so once again this lambda is a user tunable parameter which you will choose based on your relative importance. Okay, so WOLS, W reach and W lasso. Okay, so I will not go in any
So,
into details of, yes, yes.
Sir, I was just wondering if you could shed some light on how different are W Ridge and W Lasso. So, I mean, they're like sort of the same thing since both of them are going to be positive, since W Lasso also will include taking the modulus of every feature. I mean, every element in W.
Okay,
So, I was
fine.
just wondering different. So,
Okay, fine. So so let me explain that to you with with an example, with examples of W vectors. So let us say WOLS may look like, I'm just giving you like some numerical examples. These are not solutions to any problem. I'm just giving you an example of how the three W's may look like. So let us say that it's a three-dimensional, there is a d equal to 3, okay. Or sorry, d equal to, let me say d equal to 5. That will make it clearer. So let's say WOLS gives you solutions like this. So suppose this is your WOLS. This is unconstrained, and let us say this gives you the least possible error. Now comes W ridge. In case of W reach, it may look somewhat like this. I am not saying this with respect to any particular data set. I am just giving some possible values of these things. So W reach may retain the relative importance or the relative magnitudes of all these things, but their magnitudes will have been reduced. Like for example, somewhat like this. something like this. So as you can see that the magnitudes of that is the relative magnitudes of the different features is more or less same in both cases, but the magnitudes have come down. This is I am not saying that exactly this will happen for all data sets. So if you try out a data set like the exact things the way the difference between WOLS and W rich you will see may not be exactly like this. I am just trying to give you the spirit of what is expected. Yes,
Apa? Ah.
please mute yourself. And in case of W lasso, the corresponding W which you may expect to get may be something like this. Okay, so like here you can see that the smaller elements, they have become even smaller, they have become close to zero, but nothing much has happened to the larger elements. The large, in fact, this for the last element the magnitude has actually gone up. I'm not but okay, maybe that may not be correct. Sorry, I'm revising that one. It's like maybe you can say like this. So you can see that the that is the like if you consider the magnitudes of the different things, they have come down. That is for the magnitudes of the larger values, they have not reduced appreciably, but the smaller values they have come closer to zero. And in fact, if you want to set some threshold like say the on the magnitude like say 2 or something like that, you can actually prune away these three features and just choose the first and the fifth features. Okay, so basically like with this is a like a very toy example, but this I hope shows illustrates the difference between the kinds of W's which you may expect from WOLS, ridge and lasso.
So W rich is like more aggressive towards higher values of parameters because they get squared.
Yes,
So,
yes. So the mini project which I am giving you for this matter is that take any data set which you want, or if you want you can generate with data sets also with like using some random numbers. One is that compare the performance of or compare the or compare OLS, ridge, lasso for different lambda. So as I said, like as you change lambda, you should see that that is as you increase lambda, you should see that this error, that this part of the error, the empirical loss is going up while the structural loss is coming down, and accordingly you should see a certain structural properties be getting enforced on this W. So so this is something which you can explore. You can actually plot for different values of lambda. As you increase lambda, you can plot both the risks, and correspondingly you can actually visualize the different W's which you are getting and see how the like how the nature of the W's are changing. Okay, and another subtask of the same mini project will be that what about other norms? If instead of the L2 norm or the L1 norm or the L0 norm, if you use say if the L3 norm or the L5 norm, then what happens to W? Okay, so like for example p equal to 3, 4, 5, etc., then what is the impact of these on W? So this is something which you can try out as a mini project. I will send it by writing also. Okay, so So with
Hello, sir.
yes.
So in ridge regression, we are trying to minimize a square of every
Mm,
every weight. In
yes.
lasso, we are trying to reduce, minimize every absolute value of the weight matrix element. But why the larger values of weight matrix are not getting close to zero in lasso regression?
So like why it is not happening, so for that you actually need to see the way this algorithm actually works. That is so I have not gone into the details of exactly how this algorithm will work, but I mean I am not saying that they will not be affected, they will be affected, because ultimately the L1 value, what the L1 norm does is the it's the sum of the absolute values of all these things. So yes, so if we reduce these things, if we reduce these things further, then of course the L1 norm also will get minimized. That's a fact. But the way this algorithm works, it is that the priority for while minimizing the magnitudes, the priority will be given to those which are closer to zero compared to the ones which are larger. I mean the larger ones will also be can also get reduced. So like in fact, of course, as I increase lambda, that is, if I as I put more and more weightage on minimizing this quantity, we will find that these things are also getting reduced. But the first things, for even for low values of lambda, you will see that the smaller ones are the first to get affected. That's because of the way this algorithm actually works. So that we have not gone into the details of that, but so there is something, so one of these s's actually stands for shrinkage. What is meant by shrinkage is that, like, you try to shrink the values of some of these things, and and that ensures that the ones which are closer to zero, I mean the ones with smaller magnitudes, they get shrinked faster. So apart from that, there is also a particular kind of regularizer known as the elastic net regularizer. So this is actually a combination of both the loss sorry, of both ridge regression and lasso regression. That is to say, here there are two terms in the regularization function. Here it contains say lambda 1 times the L1 norm plus maybe the lambda 2 times the L2 norm, something like this. So this is also something you can study and try to understand what exactly it does in case of your mini project. Apart from that, also there are other norms such as the mixed norms or the grouped sparsity norms. So I will write many of those to you. Grouped sparsity is another interesting concept, where it's like the different attributes you have, you may try to define some groups of attributes. Say let me just draw this example. Say, let us say that there is this is your w1, w2, w3, w4, w5, w6. Okay, let us say that these are your six attributes which you have. The w6 may stand for bias, or like you just consider these 5 attributes. Now it may happen that these two attributes form one group, these two attributes form another group, and this lone w5, this forms a third group. So like you may be interested in choosing a small number of these groups of attributes. That is to say, you may choose either w1 w2 and the others are all 0, or you may choose w3 w4 and the others are 0, or you may choose just w5 and the others are 0. Now that that is the you are not actually trying to make the vector fully sparse, but you are trying to make it group sparse. That is, one group will be present, the other groups will become 0. So that is called grouped sparsity. So like in certain applications, the need for grouped sparsity may arise. So how to so like you may also consider in your mini project like which kind of norms or what kind of regularization I should go for if I want group sparsity. Okay, so I'll send you the statement of the mini project after this class. But now for the sake of time, let's move on to our next topic, which is about probabilistic classification.
Sir, why lasso norm is not differentiable?
So I'm not saying it's not, it's differentiable, but like if you differentiate it, like get it, that is what in case of like in case of ridge regression, you actually saw like what you did is you solved this problem, right? You solved del w with respect to 0, and you actually got an expression for w like this. In because this includes the L1 norm of w, if you try to take the derivative of the L1 norm here, then you will not be able to get a clear answer like this. Because what is the L1 norm? L1 norm is the magnitude of W1 plus magnitude of W2. Sorry, let me write it. L1 norm is like this. This is basically equal to, right? So can you, so now if you differentiate this thing with respect to W, what will you get? Right, you can like you cannot really get it do this kind of a derivative. So that is the problem which arises. So we have to go for some other numerical optimization methods.
Sir,
Yes,
sir, for this mini projects, whom can I ask for the doubts if I have any?
you can ask me.
And when can I ask you, sir? During the
Any,
lab hours or during the
you
classes?
can drop me mail. You can drop me mail, or you can drop a text in the chat box. I mean the personal chat of MS Teams.
Okay, sir. Thank you.
So now we come to a new topic of probabilistic classification. So let me just speed up because we are running late. So now let us say that whenever I am making any prediction, I want to like attach a probability value to it. That is to say, instead of just say, like in case of classification, the way we were considering earlier, say if you consider decision tree, right? So in case of decision tree, I was just predicting the value of y based on whichever is the modal level of the leaf node where I have ended up, right? So I was giving you just a value of y. The that in case of k nearest neighbor also the same thing. I was giving you a value of y, but in whatever algorithm I use, I am never certain that whatever value of y I have given is correct. Say for example, in case of in case of k nearest neighbor, that is what I was doing is that I was taking a vote. In case of decision tree also, I am basically taking a vote in the this thing in the leaf node. So it like it may happen that I am going for k equal to 5, and I see that there are three classes a, b and c. A has got 3 votes, b has got 1 vote, and c has got 1 vote. So in that case, I can say that I have that is I am predicting the class A with 60% confidence. That is, out of 5 votes, I have got 3 votes in favor of class A. So I am giving that is my predicted level y hat is equal to A with 60% confidence. I can say this, but then it may not be a very useful thing to say, because that is the confidence which I am talking about, that is highly dependent on what value of k I have chosen, and it's also dependent on like which all neighbors I am choosing. That is that is for when I say k equal to 5, I mean that like these are the votes I have got for from the neighbors of this particular point which I am trying to predict. If I am trying to predict a different point, then I will get a different set of neighbors who may vote differently. So for different, that is whenever I am trying to quantify this confidence, in I am like calculating this confidence with respect to different neighbors in case of different points, and it the choice is, and this confidence is also a function of k. So in a sense it's like it's a bit inconsistent, that is we are not being able to there is some measure of confidence I am giving, but it's not a very clear framework. Same can be said about decision tree also. That is, I in the when I am trying to classify a particular vector with respect in a decision tree, let's say that here is my decision tree. Let's say that my feature vector my test vector first came to this node, then it came to this node, and in this node I have got like a b, the among the training examples a is the dominant class with 75 examples. Then there for b there are 50 examples, and for c there are 25 examples. So I can say that I will predict a with 75, that is I will say that y hat equal to a with 75%, or what, not 75%, right, with 50% confidence. Okay, but that 50% confidence is again with respect to only these examples. If instead of going to this leaf node, if I had gone to this leaf node on in this leaf node, then the same confidence I would have calculated with respect to a different set of training examples, right? So like while these are giving me some notion of confidence, it seems to be a bit arbitrary. So now the question is, can I like give a clearer quantification of my confidence? So for that, I start with a different set of methodology for probabilistic classification. So let us start with a simple example of a binary classification where there are two classes. So for convenience, let me say that, like that is class 1 I am denoting by 1, and another class I am denoting by 0. Okay. So like remember in our early lectures I had said that in various cases denoting the class labels by numbers like 1 0 or 1 minus 1 may give you some mathematical advantages for some of the algorithms. So for k nearest neighbors or decision tree, we had not seen any such advantage. If we had gone whatever labels we have, if we went with those labels, it was working fine. But in the algorithms which we are going to see right now, you will see that by calling the two labels as 1 and 0 actually gives you some benefits. So what happens in so now let us consider this particular scenario, a very simple scenario, that let's consider one dimensional data d equal to 1. Okay. So basically like you have only one attribute, forget the bias, like you have only one attribute, so it's basically everything is on a single axis, not even two axes, only one axis. So let us say that there is something like a threshold. Okay. And without loss of generality, I this attribute I am just calling it x, and let's say that there is a threshold, and without loss of generality I call that threshold as 0. If that threshold instead of being 0 was say 10 or minus 5 or something like that, I would just add by an offset term and make and just take care of that. So without loss of generality I can say that threshold is 0. And threshold for what? Threshold for class level. So I can say that all the points which are less than 0 like or are likely to belong to class 0. Okay. And all the points which are on this side, that is higher than the threshold, are going to be belong to class 1. Okay. not now, this is not a deterministic rule. If it were, then I would not need probabilistic classification, but I can say that the probability is that is that is there may be some outliers, like there may be some 0 points on to the right of x equal to 0 also. Maybe here another 0 point is there. Similarly, on this side there may be a cross point, the cross means, in this case, cross means class level 1 and circle means class level 0. Okay, so you can see that all the general rule is that on this side the cross are in the majority, and on this side, that is left of x equal to 0, the circles are in the majority, right? But if you see that is close to the threshold, there are some violations. Like for example, this circle, this has come on the right side of the threshold. This circle also has come right side of the threshold. Similarly, these crosses, they have also violated the threshold. But as we go further and further from the threshold, we see that these violations become lesser and lesser. That is, most of the violations are close to the threshold. As we go deeper past the thresholds, we see that these outliers become lesser and lesser. Okay, so this is a part is, it may be a simplistic scenario, but this is what I am I am starting with. So now if I want to quantify this, what is the probability that y equal to 1 given a particular value of x? Okay, so this is what this is the quantity I am interested in. I want to for any given point with whose feature value or attribute value is x, I want to define this quantity, the probability that its class level is 1. Okay, so if I now plot it, if I plot this as a function of x, right? So what does that plot looks like? Let's see. On the horizontal axis, I am plotting x, the attribute value. On the vertical axis, I am plotting the probability that y equal belongs to one particular class, the class 1, given the value of x. Okay. So can you tell me roughly what will be the nature of this plot?
Sigmoid function.
Sigmoid function. Okay, what is sigmoid function? You are jumping many steps, so tell me what is sigmoid function? Okay, for low values of x, should, that is, say for so this is x equal to 0. So for x equal, say x equal to minus 10 or something like that, should this probability be high or low? Now since it's a
Close to
probability,
0.
so since it is a probability, it must lie between 0 and 1. So as you said, for here it must be closer to 0. Okay. Then for x equal to minus 5, it's still close to 0. Then so like as I move rightwards, it's then what happens as I move rightwards?
It will increase.
It increases. It gradually increases. Okay. Then what happens? As I reach x equal to 0, what happens? Once I cross, like what do you think its value will be at x equal to 0?
0.5.
It should be 0.5 the way I have defined it. I have said that on the left side, its probability is it's likely to be 0. On the right side, it's likely to be 1, and like, but close to the threshold, there will be certain violations. So like on balancing out the different kinds of violations, it may be quite reasonable to assume that at x equal to 0, like both classes have equal probability. So like this. So like the probability, as I increase x beyond the threshold, the probability of getting y equal to 1 keeps on increasing, and then what happens? Then what happens?
Tends towards 1.
It tends towards 1, so it's really like this. So this is the nature of the curve which we see. So like it's initially it takes a low value for a long time, it's close to 0. Then as it approaches x equal to 0, it gently starts rising. It rise at x equal to 0, it reaches 0.5. Then it rises a bit further, and then it flattens off like this. Okay. Now, as someone already said, that this kind of a curve may be approximated by what is sometimes known as a sigmoid function. I am not saying that this function is necessarily the sigmoid function, but there is a function which is called the sigmoid function which has roughly the same behavior. Okay, now since it is 6 minutes past 9, I'll take a 5 minutes break, after which we will continue this.
Hello, sir.
Yes, please tell me.
Sir, in AI Shiksha website, I'm not able to get in Jupyter instance.
There is
I
that
refresh.
SageMaker,
Yes, sir.
right? It's not starting up. It's a common problem. Like we have brought it to the notice of the developers. Like they are trying to fix it. It will take a bit of time because that platform is not yet ready to take the load of a such a big class. So so please bear with it. Like like in case you are not able to submit it on time, that is you are not able to start the SageMaker and before the deadline, in that case you simply mail the mail your that is like all the members of that group may mail it to that mail id called mlfa.assignment@gmail.com, and that will be
Sir,
fine. Yes.
but how will we check if our answers are correct or not? Because we
The
can
TS
only
will
check
correct it.
them.
The TS will
Sir, but we will not know prior to that, because in SageMaker, if we have if we submit, we will get a score and we could improve that score as well. But if we just
right,
submit,
right. So
hmm,
you do as best as possible. We will make sure that is you try to get as best as accuracy as possible, and with that you submit it. So don't worry. We'll make adjustments for that.
Uh, Excuse me, sir.
Yeah.
One of our team members has submitted it on SageMaker, but the rest of us are not able to open the platform. So, we all should mail you, or it is fine
just
that
drop
one of.
just drop a mail to mlfa.assignment saying that telling the name of the person who has submitted on SageMakers, and mentioning the names of the others who could not submit it. That will be fine.
Oh, okay. Sure, sir. Thank you.
sir,
Yeah.
can you send us the answer array which we have to fill in the assignment so that we could compare it ourselves manually?
No, that comparison will be done by the TAs. You try to do your best. Based on that, will be evaluated. It's okay if your answer does not match perfectly match the answers that are expected by that script.
Sir, would you please write that email ID in the chat box?
I will send it to you by by a proper mail after the class. But still, if you want, I am writing that.
Yes,
So, everyone has to submit the assignment in group.
Ideally, yes, but since so many people are having problems with SageMaker, like it is okay if like one team member submits and the others just and a mail is dropped to this mlfa.assignment@gmail.com stating what has happened. Okay, let's come back. So like as I said earlier, so this is the nature of the curve which we will get for probability y equal to 1 given x. So as somebody noted that this is the sigmoid function. So that's a correction is that this need not be the sigmoid function, but there is the sigmoid function will looks somewhat similar to this. That so like it may be it like we may be tempted to approximate this curve using the sigmoid function like this. So sorry, that's not a good drawing. Write a bit better. So this is roughly what like if you plot the sigmoid function, this is what its curve looks like. Still it's not good. So here you can see that it lies between 1 and 0. This is, let's say, 0 and this is 0.5. So what the expression of the sigmoid function is as follows. So this is, so if I call this as x and this as y, then y equal to this is a sigmoid function. So in this case also, so like that is I may be tempted to approximate this quantity as okay, fine. Now so now these, so I was talking about the threshold now. So like earlier like if the threshold is 0, then this is what the sigmoid function is. But suppose that the threshold is not 0, the threshold for crossing from 0 to from one class level to another, let us say by any chance is x equal to b. Okay, so then in such a situation, how can I modify the sigmoid function so that this same thing is satisfied?
I can shift the axis from x equal to from 0 to x minus b.
Right, very true. So how will the expression of the sigmoid function change in this case?
So
Minus
y
x
equals to
plus
1
b.
over 1 plus minus x minus of b.
Right. So basically that whenever x equal to b, it should be the same as this, the exponent becomes 0. Right. So like x equal to b, the exponent becomes 0. So I write it as like this. Fine. So this way we can do the shift of exponent. Now let us go one step up. Let us say that instead of one dimensions, let's say what if it is two dimensions. So let us say that again let's consider there are two dimensional feature vectors x1 and x2. both can be positive and negative. So let us now consider a situation where there, instead of a point, there is a line. Okay. So what is a point in a one dimensions is a line in two dimensions. So let us say that there is a threshold like this. The expression for this line might be W transpose X is equal to plus B, W transpose X plus B equal to 0. So where, what is this X? X is nothing but a two-dimensional vector x1, x2. Right? So so what is B? B is like in this. So in B is basically a threshold. In this case, B is a real number where the threshold, where the threshold lies. In case of in this case, the B which I am talking about is, okay, instead of B, let me call it as C, just to avoid confusion. This C is the usual intercept. So at that is like you know the slope intercept form of the straight line, right? So like this is basically just a different way of writing the equation for the straight line. Like you may know the equation of the straight line to be, say, x2 equal to mx1 plus c. So, or say ax1 plus bx2 plus c, something like that, equal to 0. So this ax1 plus bx2 plus c equal to 0, this may as well be written in the form w transpose x plus c, where w is this vector a, b, and x is this vector x1, x2, and c is what you just call as the intercept. Okay. So now what happens is that, what happens in this case is something analogous to the previous case. On this side, most of the points are crossed, that is to say plus 1. On this side of the line, most of the points are circled, that is to say 0. But there is a difference. The difference being that there are some threshold, there are some outliers which are like this, and also some outliers which are like this. And as I said earlier, the thresholds are these outliers are concentrated near the threshold line. In this case, if they were concentrated near the threshold point like this. In this case, they are concentrated near the threshold line, and as we go further and further, they become rarer and rarer. Okay? So this is like just the two-dimensional analog of what I said earlier. Clear? So now, so now what happens? So now what I am trying to say is, I am again trying to like get an expression for this quantity. What is x in this case? X is, as I said, it's a two-dimensional vector x1, x2. So instead of a single scalar of value of x, in this case, x is the two-dimensional vector. So what I am asking now is that, given a particular two-dimensional vector, which basically means given any particular point in the two-dimensional space, I am asking you what is the probability that y equal to 1. Okay. So now, so as you can understand, the way I have defined the problem, this probability will be quite low for points which are far away from this line on this side, which lie on this side of the line. This probability will be very small, and for those points which lie far away from this line on this side, this probability is going to be large. So from the knowledge of coordinate geometry, let me draw this afresh. So from the knowledge of coordinate geometry, you already know that if you consider this line, the equation of the line is W transpose X plus C equal to 0. That means every point on this line satisfies that equation. But what about the points which are not on this line? Say the expression, so this is x1, this is x2. Equation for the line is W transpose X plus C is equal to 0, and so like W is some two-dimensional vector, let's call it as W1, W2, and similarly X is equal to X1, X2. Sorry, is anyone saying something? So for like for all points on this line, this is going to be satisfied, right? For all points on this line, this is going to be satisfied. But what about?
Sir,
Yes.
sir, in W vector, like you have put W1 and W2, right? Like
Yeah.
instead of W1 and W2, we can put like 1 and W1, right? Like you
That
have
also you
make,
can do. That
yeah,
also you
like
can
you
do.
have make three parameters. Like in that three parameters, one we can put as one.
Yeah, definitely. That also you can do. That is the same, basically the same as the convention we are using in the other case. That like yes, definitely we can do that also. So okay, so let's use that convention only. Let's just forget about C. Let's just write the equation of the any line as W transpose X equal to 0.
There will be a plus one, right?
Hmm? So what happens to those points which are on these like on which are not on the line? For all the points on the line, this is satisfied. But what happens to the points which are off the line? So on one side it will be W transpose X greater than 0. On the other side it will be W transpose X is less than 0. If you consider any point which is off the line but on one side, this will happen. Now, regardless of what is the exact magnitude of W transpose X, it will be positive on all points. On this side, W transpose X will be negative. Correct? So now what I am saying in this case about the labels of the point is that for on this side, most of the points are going to have this one label of 1. Similarly, most points on this side are going to have label of 0. Okay, except for some outliers. It's because of these outliers that there is some uncertainty. Had it been had there been no outliers, then like we would just make a deterministic rule like this. If W transpose X is positive, then you classify the point as cross. If the W transpose X is negative, then you classify the point as circle. I could have said that, but I am not being able to say that because of the presence of outliers like this, and these outliers are bringing me some uncertainty. In this case, actually it may not be fair to call these points as outliers because I am assuming that there are a significant number of them. Outlier is like something which is typically quite small in number, say below 5% or something like that, but here I am assuming that there is a non-negligible number of outliers. So what I can say is that so basically the thing which I am interested in once again is this quantity. This quantity. So in this case, X is not a single number, but it's like a feature vector, and I am trying to quantify the probability that it is equal to 1. So as you can understand, for those points for which this holds, this probability is going to be higher, and for those points or I mean closer to 1, and for those points for which this holds, there this probability will be lower, that is closer to 0. So what I and higher the value of that is also I also know that for points which are close to this line but on this side this probability is high, I mean is relatively high, and as I go further and further I'm sorry, I said the reverse thing. For those points which are on this side of the line but close to the line, this probability is somewhat lower, that is close to 0.5. But as I go further and further, deeper and deeper into this side, or this, as I call it, this half space, this probability increases. Why? Because the probability of there being these violating points, these decreases as we move further and further from the line. So this probability also increases. Similarly, when I am close to this line but on this side, this probability is closer to 0.5. But as I go deeper and deeper onto this side, this probability becomes smaller and smaller. Okay. So again, this is a fit case for applying the this function which I called as the sigmoid function. E to the power minus, so instead of writing like in the previous case I was writing e to the power minus x, or maybe minus x minus b or something like that, instead of that let me just write w transpose x. Okay. So you can convince yourself that this makes sense. So because for all, like at so like in the previous case, at the threshold was at the threshold, what happened? The threshold, this exponent had become 0. So at the threshold we had got 1 plus e to the power 0, which basically meant 0.5. Right? In this case, the threshold is not any point but this line itself. But what's the equation of this line? The equation of this line is w transpose x equal to 0. So whenever I reach any point on this line, what is the probability? What is this probability equal to?
Half.
Half. 0.5. Because for such values of x, this w transpose x becomes equal to 0. So I write 1 plus e to the power 0, which is half. And then as I move further and further, deeper and deeper into this, on this side, my w transpose x becomes larger and larger, which means the exponent of e becomes smaller and smaller. And as the exponent of e becomes smaller and smaller, the whole thing becomes closer to 0. So I come closer to 1 by 1, that is 1 itself. Of course, it will never become exactly 0. E to the power something can never be exactly 0. It can only tend to 0. So I can say that this tends to 1 as w transpose x tends to the positive infinity. Right? That is, if as I move further and further away from this line towards infinity, w transpose x also keeps on increasing. It tends towards the positive infinity. So this probability becomes or tends to 1. Similarly, as I as I move deeper and deeper on this side, my w transpose x tends to what? What does it tend to as I move deeper and deeper on this side?
Minus infinity.
It tends to the negative infinity. So this thing, and what happens to the corresponding probability? So as this becomes closer and closer to minus infinity, this like this so what happens to this whole quantity? It actually, similarly this quantity also, yeah, so this quantity also, the denominator also tends to infinity, the positive infinity, which means that the whole thing tends to 0. So we can say that this probability tends to 0 as w transpose x tends to minus infinity. Okay. So I hope this system is clear. That is, as I go, there is a threshold line like this, which which is indicate whose equation is W transpose X equal to 0. Now that line basically divides the whole 2D plane into two half spaces. One is the positive half space, the other is the negative half space. In the positive half space, like when I am close to the line, there is a probability of encountering some negative point or some points with class level 0, but that probability decreases as I go deeper and deeper into the positive half space. That is to say, the probability of y equal to 1 increases, keeps on increasing and tends to 1 as W transpose X tends to infinity. See, the same thing can be said about the negative half space, that as I go deeper and deeper into the negative half space, W transpose X tends to minus infinity, and similarly, the probability of encountering a point with class level 1, that is a cross point, it tends to 0. Okay. Now this thing I had done for one dimension earlier. Now I am showing for two dimension. There is nothing which stops me at two dimensions. This whole thing continues at three dimensions also, four dimensions, five dimensions, any d dimensions also, I can say this. So the only difference will be the dimensionality of W and X. So that is like, but W transpose X equal to 0, in case of two dimensions, it is a line like this. For three dimensions, it will become a plane. In higher dimensions, it will become a hyperplane, and so for in case of four dimensions, it will become a four-dimensional plane or a hyperplane. In case of five or dimensions, it will become a five-dimensional plane or hyperplane, and so on. So, but whatever it is, whatever dimensionality I am considering, this W transpose X equal to 0 can be considered as the threshold. Okay. And so this whole treatment will continue as it is as we go into higher and higher dimensions. Not just for one dimension or two dimensions, for three dimensions, but for any dimension this will work. Okay. So now you may see that what I have done here basically is I have done something like a regression. That is the value, the quantity which so what was the definition of regression, if you remember? What I am, in case of, what happens in case of regression, there is a d-dimensional feature vector X which lies in the d-dimensional real space. In case of regression, what I do is I map it to a real number. Sorry. So the label space, in case of regression, the label space is the real space. That's how what I had defined for regression, and based on that we had done linear regression, ridge regression, lasso regression, etc. So in this case also I am doing something like that only. I am taking a feature vector X which lies in the feature space. In case of regression, this need not be the d-dimensional space. That's the case in case of linear and ridge regression. This can be this. This is basically the feature space, which, as we said, as we saw earlier, it need not belong to any of the standard spaces that we are familiar with in mathematics. But for linear regression, we'll insist that this feature space is also the d-dimensional real space. Here I am so this here in this case I am again making the same assumption that this X, the feature space X, is the d-dimensional real space. So what I am taking is that I am taking any feature vector X from the feature space, and I am mapping it to what? To a probability value. So it's basically a number between 0 and 1, which is of course definitely a real number. Okay. It's a real number, but not any real number. It's a real number between 0 and 1. In fact, like we can say both sides included. Okay. So in a sense, what I have done here is a specialized form of regression. Instead of regressing onto the entire real space, I am regressing it to only this space of 0, 1. Okay. And what have I used for the regression? I have done the regression using the sigmoid function, or which is sometimes also called as the logistic function. So in previous case, in case of the linear regression, what I had done is I had taken any real vector x from the real space, and I had mapped it to the real space by in this way. I had used the linear function to map that x into the real space. This is what I did for linear regression and also for ridge regression, lasso regression, etc., which are just extensions of linear regression. In this case, what I am doing, I can call as logistic regression. Why is this regression? Because I am mapping the feature vector to the real space. That is the input is a feature vector, the output is a real number. That's why regression. Why logistic regression? Because I am, instead of using the linear function, that is I have to map from the feature space to the real space. So in case of here, when I did that mapping with the help of a linear function like this, I called it linear regression. Here I am doing that mapping with the help of the sigmoid or the logistic function. So I am calling it as the logistic regression. Okay. So this is the logistic regression, and the nature of the logistic regression is of the logistic function is such that the value, it will always map me to a value in this range from 0 to 1, not to any arbitrary value in the real space, but only to those values which lie between 0 and 1. And it is my good fortune that this range 0 to 1 is also consistent with my requirement of the probability. So we know that the probability of any probability value must lie in this range 0 to 1. So that's what the logistic regression is achieving for me. So using this logistic regression like this, I am able to do the this probabilistic classification. That is, I am now not only, so given any function x, given any feature vector x, what I can now do is I can actually give you values like this. Probability y equal to 1 is equal to 0.7, and probability y equal to 0 given x is equal to 0.3. Okay, this I am able to achieve for you. So note that I like what I like, unlike the previous examples of k nearest neighbor or decision tree, here the probabilities which I am calculating is not on the basis of some small set of neighbors or examples which I have considered, but on the basis of the entire data set itself. Right, that is like later we will see that I need to find what is this threshold. But once I know what that threshold is, this threshold is something like it's an universal thing. It's not not that this threshold is not defined with respect to any individual point or any individual set of points, but with respect to the entire data set itself. So that way we can say that this is a better way or a more holistic way of probabilistic classification rather than say k nearest like k nearest neighbor or decision tree or something like that. Okay. So what the entire data set is the training set then. Okay, so I will clarify this point. Thanks for asking that. No, the entire data, so like this thing has been calculated on the, like what I am showing you right now is the training set only, but the testing set will be further points which we'll talk about it in a minute. Please wait. So so this way you can attach probabilities to the two classes. Now suppose instead of a binary classification, suppose I want to do a multi-class classification. That is, it's not enough for me to classify it into one of these classes, but suppose I want to do y equal, let's say that there are multiple classes like this, let's say a, b, c, d, etc. Now what I am going to do is now I can generalize it. Now that I have got my framework ready, I can generalize it in the following way. Probability y equal to a given x, I can write it as before writing that expression, let me just rewrite this in this sigmoid function. So here you can just see that I can rewrite it as follows: e to the power w transpose x by 1 plus e to the power w transpose x. Okay. Clear? You can just understand by multiplying both sides by e to the power, I mean both the numerator and denominator by e to the power w transpose x. Now what I am saying is that I will define a function like this: e to the power w a transpose x divided by e to the power w a transpose x plus e to the power w b transpose x plus e to the power w c transpose x plus e to the power w d transpose x. Fine. So so if there are four classes like this, or k classes, instead of having just a single w, I will actually have four w's: wa, wb, wc and wd. For each of the classes I have like a w vector like this, and the probability which I am calculating for each of the class can be obtained in this way. So for the probability for any class is basically proportional to e to the power the w of that class transpose x divided by the normalizing constant. This denominator only makes sure that if you add up all the probabilities of all the classes, you get 1. So that's the purpose of this denominator. The main so just like in this case, just like you could say that this probability is proportional to e to the power w transpose x, here also you can say that the probability is proportional to e to the power w the probability of in any particular class is proportional to e to the power w of that particular class transpose times a. Yeah, and then the proportionality constant is defined accordingly. Okay, I hope this matter is clear. Now, so but that may cause a bit of confusion, because earlier so far I was like I had motivated this kind of logistic function. Yes.
Sir, this line that we are drawing, it has been drawn between two different classes, right?
Right.
So like when we are writing this e to the power W A transpose, so shouldn't it be W A B transpose?
Sorry, should you write?
Shouldn't it be W A T transpose, W A B transpose?
Okay, so this matter will become a bit clearer when we go into one versus one and one versus all classification. So please bear with me for like one or two more classes before we clarify this issue. Basically the problem is that in this case we are considering that there are two classes and there is a threshold line between them. The entire treatment was based on that. Now here the matter has suddenly been complicated by the introduction of four classes or more than two classes, and that's why I am saying that like now for each class you have a this kind of a thing. Now so you may ask now that okay, so what is the earlier the w which we are considering was a threshold between the two classes. Now what is the threshold between? That is so if there are four classes, then there will be like between every pair of classes that there will be one threshold, right? So there should be 4C2 equal to 6 threshold like this. So instead of saying A, I should ideally be talking about AB or AC and things like that, right? But let us postpone that discussion. So as of now, let us just say that this is in case of multi-class classification, this logistic regression can be done like this. Now the question then arises, as was already asked, that just a second. So let's now come to this point that then what is the learning problem involved in this case? What is the training set? What is the training problem involved in this case? The training problem is the problem is that when you are given your training data set, sorry for the bad drawing, so let's say the problem is that when you are given the data set for training, you do not know what exactly the W is. That is where exactly that threshold line lies, or the threshold point lies, or the threshold plane lies. You only, like, you are given a data set like this, something like this, but that is you have like, for some reason you have like, you are able to guess that there will be a threshold such that the like, on one side the points will be mostly cross and the other side the points will be mostly circle, but you don't have much idea of what that threshold is. That is to say, you do not know W. You know everything, that is, in the training points you know X as well as you know the corresponding Y, but you do not know W. So basically you have to calculate W. That was the case in your linear regression also, right? You had a X, you in the training phase you knew X, you knew Y, but you did not know W. So in the test, so in this case also it's the similar situation. You know the locations of the different points, you know the presence of Y, you also have some reason to think that there is a threshold like this, there is a threshold line or a threshold plane like this called W transpose X equal to 0, such that on one side of it the probability of one class will be higher, and on the other side the probability of the other class will be higher, but you do not know what that W is. So what is your task? The task is to estimate W. Fine. So now the question is how to estimate W. So if you remember what we did in case of linear regression, the same steps we are going to do in case of logistic regression also. So what did we do in case of linear regression? We defined a loss function. The loss function, which is a function of W. In case of linear regression, the loss function was the difference between the predicted level and the true level, which I wrote in the following way. Right? In this case, the thing is that a problem is arising because like, what you have is the label is either 1 or 0. Okay, the label is it's a classification problem. So although you are going for logistic regression, it's basically a classification problem because there are only two class levels, 1 or 0. Unlike regression, the class levels are not real number. The class levels are binary, 1 or 0. But what you are predicting is a probability which lies between 0 and 1. So here is a potential mismatch, that is, you cannot really compare the label with the output, with the with the true level with the predicted value, because what you are predicting is a probability distribution, right? You are predicting something like 0.7 as the probability of class 1. But what is what is your level? The level is class 1. Okay, so that is, you cannot really compare a class level with a probability. So what we have to do? What we do is it's not that difficult either. I compare, like I just convert the class level into a probability distribution. My output is a probability distribution. So like in the, like you may say 0.7, 0.3 is my probability distribution. The distribution over the two classes, say probability of class 1 and probability of class 0. I just transform my input, so that like input data, so that my predicted output, sorry, the true output is also a probability distribution. So how do I do that? Any idea?
We can make a line, a line which will be like of least distance from both the all the points.
No, that comes later. That comes later. As of now, I am only asking you how the main problem I am facing right now is how to compare the label, or the true label with the predicted, with the output of my model. The output of my model is a probability distribution over the two classes, and but the true output is just a class level, either 1 or 0. So how can I compare a class level with a probability distribution?
So first I pass this output through the sigmoid function and then get the probability, and then yeah, that's how, and I just subtract this or
Okay.
take the mean.
Okay. Any other answer? I will give you a hint. So this is y equal to 1. This is your true level. Now, based on, so this is your class level. So can this be expressed as a probability distribution?
So one hot encoding.
Exactly, one hot encoding. You can say that the 1 0. So you can like it's like it has been given to you that the, in this case, the probability of belonging to class 1 is 1 and the probability of belonging to class 0 is 0. In like this is what was this is your true input, like the true output, right? And that predicted output is this 0.7, 0.3. So now what we have got is that my true output is a probability distribution like this. My predicted output is also a probability distribution like this. So now basically what I have to do is I have to like compare two probability distributions. Okay. So now, so basically I have, so let me say P1 and P2. When I have P1, like I have two probability distributions P1 and P2, I can, in a sense, I can define various quantities on them, or define various measures on these two probability distributions, and these measures will be small, such that the measure will be small if the probability distributions are in some sense close to each other, or and it will be large if these probability distributions are like far apart from each other. Now what I mean by close or far may be different, but in general you can understand that, say this is 1 0 and this is 0 0.7, 0 0.3. Okay, so this is my P1, this is P2, and my P3 is as follows, 0 0.2, 0 0.8. Okay, P3. So intuitively it should be clear that P1 and P2 are closer than P1 and P3, because in some sense P1 is P1 is saying that it is only the first thing will happen and the second thing will not happen deterministically. P2 is saying that the first thing is likely, but the second thing can also happen. The P3 is saying it's the second thing which is almost sure to happen. So in a sense that P1 and P3 are contradicting each other, but P1 and P2 are roughly agreeing. So we can say that P1 and P2 are closer to each other than P1 and P3. Even though how I measure that closeness is a different matter, but so this example shows that there is a concept of closeness between probability distributions. Okay, so now based on this I define a concept known as cross entropy, which is like which is defined in the following way. So minus How do I put it? So let me put it in the following way. Y P P1I log P2I. Now what is K? K is the set of possible values which can this random variable can take. In this case, of course, it is 1 and 0. So in general, for any random variable which takes K values, so this probability distribution, each of these probability distributions P1 and P2, they will have K different values. So this is the way I have defined the cross entropy function. So like in your, while we are studying decision tree, we had already seen the entropy function, right? That is, we have our probability distribution like this, say 0.7, 0.3. So that what was the entropy of that? The entropy of that this distribution I had defined in as what? What was the expression of entropy? Can you tell me?
Minus pi log
Minus
of
P log
pi
P.
Minus point,
base 2.
so 0.7 log of what?
0.7
Log of 0.7 base 2.
Then
Minus
minus 0.3 log point.
point.
right. So there I had only one probability distribution which I called as P. So what I wrote it in the form of Pk log Pk summation over K and the minus sign here. Okay, this is entropy. Now what I am saying is there are two probability distributions, P1 and P2, and or if you say P and Q if you want to call it. Okay, to just to avoid the confusion with of notation, let me call it P and Q. And here also let me write it accordingly. Right, so see like here I was writing it as summation over pi log pi. Here I am writing pi log qi. Okay, so because they are so this is entropy, this is cross entropy. So in this case, my loss function is defined as the cross entropy loss function between the true level, the true distributions and the predicted distributions. So what is pi? This is the true distribution, and this qi, this is the false distribution. Sorry, not false distribution. What am I saying? This is the predicted distribution. Okay.
So,
Yes.
can we say that K is the dimension of label space?
Yes, definitely. Absolutely, you can say that. K is the dimensionality of the label space. Now, if I come down, so this is the cross entropy loss function. So now the question arises, what do I now need to do? I need to choose, like select W so as to minimize this the total loss function, and that is not over, and that has to be done over all the points in the training set which we are considering. So let me just change the notations a bit. Each of the dimensions let me denote by small k as earlier. So I'll write it as pk and this as qk, and then I will repeat this analysis for all the data points. There are n data points, and for each of the data points, there for the ith data point, like I have a true class, like a true distribution over the label space and a predicted distribution of the over the label space. So I write it accordingly. Okay. Now, the question is, how so basically I have to optimize W here. Now PIK, this is something which I get from my data set. So if the label if yi is my rule is that if yi equal to k in the data set, if yi is equal to k, then pik is equal to 1. That is the precisely the one hot encoding which I have done. This is the rule of one hot encoding. Okay, so yi so which also basically means that pik is either 1 or 0, and it is coming directly from the data set. There is it's just a function of y, nothing else. But qik, where am I getting qik from? Qik is coming from my from the logistic regression. So qik is basically it is proportional to the way I had written it, minus wk transpose what? Transpose xi. Let me write it more clearly. I'll just continue for 5 more minutes. Those who have classes may leave because the recordings are anyway available. So qik is proportional to the probability of that particular class, which I have already expressed in the following way. So each class has its own w vector. So I write it in the following way. So remember I am using xi because this is the ith data point. Okay.
The e power plus, there will be plus.
Where?
E power plus will be there, right?
E to the see, consider the logistic function in the sigmoid function. Yeah, sorry, it's not minus, it's plus. Correct. Thank you. Right. So now if I just go back to the simple case of k equal to 2, that is binary classification, then you can try to figure out what this loss function is reduces to. In that case, the loss function reduces to, we take it over like all the data points equal to 1 through n. So for the ith data point, what do you get? You first of all you get pi 1 log qi1. But what is what is qi1 in case of binary classification? qi1 is nothing but the sigmoid function itself. So it is written as e1 plus 1 by e to the power minus w transpose xi, right? Because if in case of binary classification, I do not need separate wk's for each of the classes. One w is enough for me, right? So I write it in this way. So so instead of this is my qik, right? So sorry, this is my qi1. Okay. Now instead of writing this whole expression here, let me just write it as in the following way. Let me write it as sigma w transpose xi. Right? It's a sigmoid. Sigma includes the sigmoid function. And what is the argument of the sigmoid function? Simply whatever is the exponent of the e. So I write it in this way. So here I write pi1 log the qi1, and the qi1 is nothing but the sigmoid of w transpose xi, right? Plus what? Plus pi2 or pi0 if you call it pi0. So the two classes I am calling as the class 1 and class 0. So pi0 log qi0. Now what is qi0? Quick. qi1 is like I know that there are two classes only in this case, the class 1 and class 0. For class 1, the probability is qi1, which I have already written, right? So what is what?
1
Yeah.
So 1 minus q.
Exactly. The qi1 is the logistic is the sigmoid of W transpose X, and qi2 has to be 1 minus sigmoid W transpose X, right? So I write this as pi0 times log of 1 minus sigmoid W transpose Xi. And now I close the whole thing. So this is the loss function which I have got for logistic regression. So as someone was asking earlier, like, do I assume that all the points are the training points? No, that you do not assume. That is, on the basis of the training points, you have to estimate W and then use that W to make further predictions on the testing points. So now how will I estimate W? By optimizing this or by minimizing this whole quantity, by this whole loss function. Okay. So now the question is like in just so note that I have followed the same steps as I did in case of linear regression. In case of linear regression, I first defined my loss function which was the squared error loss. This one for linear regression. And then I minimize this to get the WOLS. In this case also, like I did the same thing. I defined my loss function, but the least square loss did not make much sense in this case because I am comparing probability distributions. So instead, I considered the cross entropy loss, which gave me this kind of peculiar looking loss function. So now what I will have to do is I will have to minimize this loss function, and that will give me the value of W which I want. So I may call that as the W log or the W logistic, right? And once I get the W logistic, then on my prediction, like when I get any new test point, I can carry out my prediction on the basis of that. That is to say, I will simply calculate the probability of the different classes by just replacing this W by setting the value of W as W log. So if you come to the testing phase, this is what the whole thing looks like. Those who have class right now, please you can please leave, because all the recordings will be available, all these materials are also shared, so please feel free to leave the class. I'll just finish in 1 minute. So if you consider the test phase, in the testing phase you will get like a feature vector which I called as X test. So you will predict the probability that Y test is equal to 1 given the X test, and this is nothing but sigmoid of W log transpose X test. Okay. So how did you get W log? W log you got by minimizing this whole thing. Now how do you minimize this loss function? So just like in case of lasso, you cannot minimize this loss function by taking derivative with respect to W and equating it to 0. You will find that because these logistic functions are involved, taking the derivative. I mean, you will be able to calculate the derivative, but you will not be able to solve that expression for W. Just like we, in case of linear regression and ridge regression, I actually got a closed form solution like W equal to some weird expression I had got, but still I had got an expression. In this case, even that you will not be able to get. So what we have to do is that this minimization will have to be done with the help of gradient descent or some kind of other numerical optimization. Now, how exactly that is done? That's a matter of one of our subsequent classes. Okay, thank you everyone. So tomorrow is our lab class, but tomorrow a new set of assignments will be given, but since we are slightly lagging behind and I need to finish the portions, so tomorrow after the lab, like during the lab hours, from 3 to 4, I will continue this lecture on probabilistic classification. So from 2 to 3, the lab assignments will be explained to you by the TS. From 3 to 4, I will take an extra lecture to finish off this portion on probabilistic classification. Okay, thank you.
Thank you, sir.
Sir, could you repeat why did you use cross entropy?
Why did I use the cross entropy loss function? So basically, whenever what I need to do is I need to construct a loss function between the predicted, which compares the predicted level and the true level. That's the definition of the or the predicted value and the true value. That's the definition of loss function. In this case, the value which I am predicting is basically a probability distribution over the class levels. That is, I may of course say that I am predicting that is like whichever class has a higher probability, I can just use that as my predicted level and compare it with the true level. But in a sense, that is throwing away some information. That is, it's not that I am, my prediction is not exactly any class level, but it's the probability of the different class levels, right? So since the prediction is a probability distribution, I have to compare it probability. That is I cannot define a loss function between which compares apples and oranges. I will have to first map the apple to an orange, and then I will have to compare two oranges. So in this case, my apple is a class level 1, 0, etc., and my orange is a probability distribution over the different classes. So what I do is I convert the class level into a hard-coded probability distribution, which has like 1 in one point and 0 in all the other points, so that now I have two oranges, namely two probability distributions. So now I can compare them using some measure which compares two probability distributions. So one such measure is the cross entropy. Okay, so I hope that answers your question. So regarding the AI Shiksha portal, I know that there are lots of problems in submitting the assignments. In fact, like that's not unexpected, since we are trying to build this AI Shiksha portal to be rolled out to a large audience. So initially there will be glitches. So I apologize for the problems, but like if you bear with this for maybe 1 month or so, hopefully they will be ironed out. For those people who have not been able to open that SageMaker for submission of the assignment, I already made this rule that they can mail the Python notebook to the TS. I will so immediately after this I am going to write a detailed mail explaining what has to be done in such cases. Okay.
Sir, why didn't we consider higher probability as predicted?
Sorry?
Why didn't we consider the higher probability?
The label with the higher probability as the predicted value. Why didn't we consider that? Right? That's what you are asking.
Yeah. Why are we?
Yeah, we can do that, but the strength of this algorithm is that we are not predicting a single level, but rather we are actually giving a probability distribution over the different levels. So we are doing more than just predicting a level. In case of k nearest neighbor or decision tree, I had only predicted a level. In this case, I am doing something more. I am actually predicting a probability distribution. From that, you can figure out your with whichever level you want to. So if I if I ignore the probability distribution and focus only on the modal level, then basically I have in a sense I have just negated what the hard work which I did by bringing in the logistic function. The aim of the logistic function is to create a probability distribution. So if I do not consider it in my loss function, I have, in a sense, I have thrown away the importance of it. Besides, also look at the nuances of the probability value. That is, in some situations, my predicted value may be my predicted distribution may be 0.9 for one class, 0.1 in for other class. In another situation, my predicted value will be 0.7 for one class, 0.3 for another class. If I am not considering the probabilities and only considering the modal class level, I am failing to make the distinction between these two cases. So I actually want these probability values to be taken care of. So even if that makes my optimization more difficult, I still want that. So that is why I am not considering only the modal value. I am going for the probability distribution.
Sir, in the logistic regression, for multi-class, like let's assume four classes, so we four probability distributions, right, for each W.
It's not for probability distribution. It's a probability distribution over four different things or four different classes. But for each of the, but there are but in the way we saw it, there are each class will have its own W. So there will be more parameters in the model. So if the classes are A, B, C, D, then for class A there will be a parameter WA. For class B, there will be a parameter WB and similarly WC and WD. But ultimately, I will get a single probability distribution also. So just to show you.
But how do we define loss function in such cases?
I will show you. Wait, just a second. So the probability distribution in that case it will be as follows. Like I will get a four-dimensional probability distributions, which is like QA, QB, QC, QD. Okay. So QA is, I will define as I will write QA as
So
e to
would
the
you share
power.
your screen?
Oh, sorry.
Sir, would you please share?
Yeah, sorry. I did not notice that I have unshared it. Can you see it? Can you see the screen?
Yes, sir.
So QA I can write in this way. E to the power some, let us say some normalizing constant D. QB will be e to the power WB divided by D. QC will be e to the power WC by D, and QD will be e to the power instead of D, because I have used D as a level, let me use something else. I'll call it as Z. Z. Okay. Z e to the power Z e to the power WD by Z. So okay. So this is my probability distribution, and I have this constraint that QA plus QB plus QC plus QD should be equal to what?
1.
1, sir.
Also, each of these should be greater than equal to 0. Right. So because we are considering e to the power something, it has got to be greater than 0. So this is already satisfied. The question now is, what about Z? So so as you can easily understand that in this case Z will have to be nothing but e to the power W. Sorry, I'll x, x, wcx, wdx. So as you can see, in this case z will be nothing but the sum of all these things. Okay, so this way we will get a probability distribution qa, qb, qc, qt. So let us say that in a particular case the numerical values of this come out to be somewhat like this. Okay, fine, suppose this happens. Now what I am doing is now so I have to compare it with my true level, which is y is equal to b. Okay, or let's say y equal to a. So if y is equal to a, then I need to encode it with a probability distribution somewhat like this: 1 0 0 0. Right, this is the hard coding. So this is my p and this is my q. So now what I need to do, I need to define the loss function, which is the cross entropy. I mean not the loss function, but the loss value, which is nothing but the cross entropy. So what is the cross entropy? Expression for cross entropy I have written as pk log qk, k equal to 1 through 4, because in this case there are 4 things, 4 levels. As someone correctly pointed out, this k, this 4 is nothing but the dimensionality or the size of the level space, which is in this case 4. So now you only tell me what is the loss function going to be, or what is the loss value going to be.
So minus log 0.3.
1 into minus log 0.3. All the others will become irrelevant because their coefficients are 0, because this p term is 0. So this is the loss I get. I hope this is clear. Fine.
Okay.
Sir, we just the formula that we derived at e power wax by z, all those stuff that we got, that we just mapped from 2 dimension to 4 dimensions, right?
Hmm.
Before
Yeah.
only 2 dimensions, 1 and 0. So the sigmoid function that we got there, you just mapped that to 4 dimensions.
The sigmoid function is like you may not be able to map directly to the 4 dimensions. So what we do is, like we for k dimensions, what we do is we get an analogy of the sigmoid function. That's what is the sigmoid function is defined in this way: sigma of w transpose x is just 1 by 1 plus e to the power minus w transpose x. Okay, so now which I can also write as e to the power w transpose x divided by 1 plus e to the power w transpose x. So this is the this is what the sigmoid function looks like. Now what I am saying is that you have k classes. So and I have, in the 2-dimensional analysis, I got this is what I claimed. I claimed that the probability of one class level is equal to the sigmoid function. Okay, so in this case, instead of saying so now let me rewrite this same sigmoid function in a slightly different way. I write it as e to the power w transpose x by e to the power w naught transpose x plus e to the power w transpose x, where w not equal to the d-dimensional 0 vector. Okay, fine. So you can convince yourself that if w naught transpose x is if w naught is indeed the 0 vector, then this is the same as this thing. Okay, so we in the, so the whole thing becomes like this: probability of one class is basically proportional to e to the power w transpose x. The probability of the other class becomes equal to, or becomes proportional to, e to the power W not transpose X. Right? Is this clear?
So,
Because
sir, in this case, we can, if we can get two weight matrices like WA, WB for two classes, then it will be similar for
exactly.
four
So like
dimensional.
exactly. So like that is if you say that there are you have two things WA and WB, or maybe if you want in this case W1 and W0, then it will be the mapping will be perfect. But that is, since we started with the logistic function or the sigmoid function for binary classification, it turned out that I did not need two things. I could do it with one thing only, but I can reinterpret it like in this way also, in the special case that W not equal to this zero vector. So now based on this particular interpretation of the sigmoid function, now I go to the multi-class by assuming that probability y equal to k given x is equal to e to the power wk transpose x. By we can so here what I am saying is that for every class there is a wk. In this case also I am saying that yes, the same thing, but that is for one of the classes that wk is equal to the zero vector. Now will this not work if w naught is not set to the zero vector? That is, if you have to still, like if you consider in this case, if you consider two w's for the two cases, yes, it will still work, but you do not need it. If like in this particular case, having one w is enough. That's all.
Sir, then for four classes also we need only three weight matrices, right?
So for that, to understand that like why you will actually need four things, in that case you will have to wait for 2-3 more lectures where we come to one versus one versus or one versus all classification. So then we will understand that even if although for two classes one is enough, but for four classes three will not be enough. We will actually need four.
Okay, thank you, sir.
Okay, thank you everyone.